Hey guys, let's go ahead and start with our section 1.8 notes. We're talking about rational functions and zeros. We're also learning something a little bit new today. So we're talking about zeros and wholes. So we see here with this function, we know it's rational because we have a function over another function. In order to find the domain, we do the same thing that we've been doing, which is to set the denominator equal to 0 and solve it. So if I take this denominator, 2x squared plus 4, and I solve it, subtract 4 to both sides, I get 2x squared equals negative 4. If I divide both sides by 2, I know x squared cannot be at negative 2. So in this case, because this x is squared, I can actually have x be anything, and it's no big deal. So the domain is going to be all real numbers from negative infinity to infinity. For the zeros, because remember, a zero is when I input a value and it gives me the value of 0 out. When we have this idea of a zero, means that if I input an unknown x, the output is 0. So in this case, with the domain, we don't want the denominator to equal to 0, but in order to get a value of 0, we can have 0 over anything equals to 0. So here's what we want to do. To find a 0, we're going to set the numerator equal to 0. So here we're going to say, okay, let x squared plus 2x minus 8 equal to 0. Well, in order to solve this, we're going to need to factor what multiplies to negative 8 and adds to 2. We know that that's going to be positive 4 and negative 2, so we'd get x plus 4 and x minus 2 equals to 0. Use zero product property to solve this. We get x equals negative 4 and positive 2 are the zeros. We can see this here in this graph. Our zeros are at 2 and 4. And we don't have any vertical asymptotes or anything. It's continuous, so we have all reals as our domain. Let's talk about wholes for a second. So sometimes you'll come across a function and it will have something like a whole. If I were to sketch this function in my calculator, it's going to end up looking something like this. I'm just going to show you first. It's going to look like a line until we get to 4, and it will have something called a whole in there, where if I pull that up in my table, on the graph it'll look like it's a line, but if I pull it up at the table, there'll be nothing there for 4. So if you're wondering, like, how does that work? How does that happen? Here's how it works, okay? Step 1, we're still going to look for the domain first, okay? So again, the domain means we set the denominator equal to 0, x minus 4 equals to 0, therefore x equals 4 is what we don't want the domain to be. So we say the domain is negative infinity to positive 4, and then from 4 to infinity. So we know we do have a break at 4, which we can see in our graph here that we don't have anything at x equals 4 right here, okay? But in order to know where a whole is, here's what that looks like. A whole is a common factor in both the numerator and denominator. So in order to find a whole, we're going to have both the numerator and the denominator factored everywhere. So in the numerator, if I'm going to factor this, I want to know, okay, what multiplies to negative 12 and adds to negative 1? I've got negative 4 and 3. So this can become x minus 4 times x minus 3. And then, of course, in the denominator, we still have x minus 4. Do you see how we have x minus 4 and x minus 4 both in the numerator and denominator? This, because it's a common factor in both the numerator and denominator, x minus 4 is a whole. We set it equal to 0, and we say, hey, there's actually going to be a whole at x equals 4. So we can actually see that here. When x is 4, we have a whole. And then the last thing that we're going to do just to find the 0 is we're going to set the numerator equal to 0. So again, here's our numerator, but we know that that x minus 4 is actually a whole. So we're just going to take what's left over, which is that x minus 3, and set it equal to 0. Therefore, x equals 3 is our only 0. And we see it, this should be positive 3 because of this right here. So this is a negative 3. And we see this 0 right here at negative 3, where it crosses the x-axis. So here's the official definition, that in order to find a 0, where we have a rational function where the numerator function over the denominator function have no common factors, the zeros of the rational function occur when the numerator function equal to 0. Okay, so vertical asymptotes, remember this is where the vertical asymptotes and the domain work together. So just as a rule of thumb, especially with rational functions, you're just going to want to factor everything that you can. I can see here and then my numerator, I can take a greatest common factor of 4 out, and I know 4x divided by 4 is x, 8 divided by 4 is 2. And then I'm going to factor the denominator. So that's what multiplies to negative 10 and adds to 3. We get 5 and 2 where 2 is negative. And this becomes x plus 5 and x minus 2. Okay, so again, with the domain, we're going to set the denominator equal to 0. So, okay, x plus 5 equals 0 and x minus 2 equals 0. Therefore, we know x equals 5 would make it equal 0, and x equals 2 would make it equal 0. So we don't want that. And we say it's from the interval of negative infinity to, what is this? Negative 5. And then again from negative 5 to positive 2, and then from 2 to infinity. And if we see this here, we know it goes from negative infinity up to, see this 5 value, there's nothing there. So there's our first region. Our second is from negative 5 to positive 2 here. And then there's our 2 to our infinity. Now, if I'm going to look for a whole, remember a whole is where we have a common factor in the numerator and the denominator. So if I look at the numerator here, x plus 2, and the denominator here, I don't see a common factor. I do see both 2's, but this is a plus and this is a minus. Therefore, it's not common. So this one does not have a whole. No wholes. Lastly, we're going to look for the zeros, and this is where we set the numerator equal to 0. So 4 times x plus 2 set equal to 0. If I divide both sides by 4, we get x plus 2 equals 0, which means x equals negative 2 as a 0. And if I look at my graph here, we see here's a 0, or an x-intercept at negative 2. Lastly, your vertical asymptotes. Remember that vertical asymptotes and the domain go together. Whatever the domain is not is where the vertical asymptotes are. So we know that's at x equals negative 5 and 2. And we can see that here on our graph. All right, let's look at this one. Again, we're going to be looking at this rational function. If we can factor, do. So I know x squared minus 9. This is a difference of 2 squares. This tells me that x times x is x squared. A negative 9 comes from a positive 3 and a negative 3 factor. And then in our denominator here, what multiplies to negative 3 and adds to negative 2? Well, this would be negative 3 and positive 1. So we get x minus 3 and x plus 1. So now that I've got that all factored, number one, let's talk about the domain. Remember, the domain is when I set the denominator equal to 0. And I get x equals 3 and x equals negative 1. Remember, I don't want it to actually be those values because I don't want it to equal 0. So we know it goes from negative 1 and 3 are excluded. So we're going to see everywhere in between and on the left and right side. So we say from negative infinity to negative 1, from negative 1 to 3, and from 3 to infinity. To find a whole, hopefully you can fill in the blank. To find a whole, we set, or we look for those common factors in both the numerator and denominator. So do we have any? We see x minus 3, x plus 3. Here's x minus 3, x plus 1. X minus 3 is our common factor. So this is where we're going to see a whole. These end up canceling out, but they do create a whole. So we say, hey, x minus 3 set it equal to 0. Therefore, we have a whole at x equals 3. To find a 0, hopefully you can fill in the blank, we set the numerator equal to 0. So what's left over is at x plus 3, and we get x equals negative 3. Remember, vertical asymptotes go hand in hand with the domain. They're kind of exact opposites. So because I know it cannot be 3 and negative 1 as the domain, those are my vertical asymptotes. Where there's not a whole, I should say. Don't repeat whole, okay? So because there was a hole at -3, we're not going to use that one, but we can say, hey, there's a vertical asymptote here at x equals to -1. And for our horizontal asymptote, remember, we're also going to look back at the original problem. So if I kind of clean this up a little bit, remember we're looking for those first terms. So we look at the horizontal asymptote. If we're comparing x squared and x squared, these have the same degrees. So we're going to look at their coefficients, which is y equals a over b, which in this case is 1/1, which is just 1. And our y-intercept, remember, is when x equals 0. Solve by plugging in for 0. So we've got 0 squared minus 9 all over 0 squared minus 2 times 0 minus 3. And we get -9 over -3, which is +3. Okay, here we go. Let's look at the next one. Example number 5. So again, we don't have the function, but we do have the graph. So a couple things I want to look at. So number 1, I see a hole. We have one here, and that's when x is 1, 2, 3, 4, 5, 6, 7. Oh, I could have also seen the domain. The domain is what is x? So let's kind of see what x is not. I see that there's this vertical asymptote here at x equals -4. So if I see the domain, it's kind of where I have to pick up my pencil. So I go forever from left to right up until -4. I start again from -4. I have to pick it up at 7. And then I start again after 7, and I keep going to infinity. So we're going to say from -infinity to -4. And then from -4 to 7, and then from 7 to infinity. So where do we see zeros? Remember, zeros are where it crosses the x-axis. Well, we see it crosses here and here, so it's at -2 and +2. We have vertical asymptotes. Remember, we said it was right here at x equals -4. We have horizontal asymptotes. In this case, we don't have a horizontal asymptote, so we say none. And then that y-intercept is happening. If I zoom in here, I'm seeing it's a little bit less than a half. So let's just approximate that at about 0.3. So we could say the y is approximately -0.3. Okay. Now, based on this graph, I just want to give you some practice with something that's kind of a new idea. This is called a sign table, where we break up the graph into different intervals where we have different signs. So, if I want to see what's the function doing between -infinity and -4. So from -infinity to -4, it's all between here and here. And we see this. These are all negative values, so we're going to put a negative in the sign graph. What's happening at -4? So at -4, we have this undefined value, that asymptote. So we know that this is undefined, or you can say that doesn't exist. From -4 to -2, do you see where this is up here? It's all in the positive direction, so we're going to put a positive in the sign table. At -2, it's on the x-axis, so that's actually where a 0 is. From -2 to +2, that's below the x-axis, so we know that's negative. At 2, we're again on the x-axis, so that's a 0. From 2 to 7, we see that it's above the x-axis, so that's a positive. At 7, this is a hole, so we know a hole is undefined, or you can say does not exist. And then from 7 to infinity, we know that's above the x-axis, so it's positive. I will show you the application of how to do this. I want you to start thinking about that, processing that there's some information that we need to see on a sign table like this. That's all for now. See you next class.